First of all, we're very honored to present our work here, which we call Panoptic-PHNet for LiDAR Panoptic Segmentation. In the Panoptic segmentation field, previous methods can be categorized into proposal-based and proposal-free approaches in terms of how to handle thing points. Regarding the proposal-based approaches, they rely heavily on the performance of an extra learning-based object detection branch, while the proposal-free approaches usually utilize heuristic clustering algorithms such as mean-shift or HDB scan, which are time-consuming. For clustering, a common practice is to predict offsets towards instance centers to shift thing points, so that the spatial distance between different instances can be increased. Here, our question is, can we obtain object-level information without object detection for more efficient clustering? Given the shifted thing points, we find that their distribution shares a similar pattern with the learning-based center heat map under bird's-eye view, which can be regarded as a natural heat map to yield instance centers. Then we get our proposed clustering pseudo heat map without extra learning tasks, being used to group all the thing points. The instance centers generated from our clustering pseudo heat map ensure the consistency between the point-level information and the object-level information. Let's go on to talk about the entire framework of our Panoptic-PHNet. We do voxelization first based on a cylindrical space partition. Then the fine-grained voxel features are extracted by a voxel encoder. The voxel features are further mapped into a size-fixed bird's-eye view image. A unit-like 2D backbone network is adopted to extract bird's-eye view features with different receptive fields. Then we fuse the fine-grained voxel features at the bird's-eye view features as the final voxel embedding to predict the semantic class for each voxel. For instance segmentation, a key nearest label transformer module is introduced to model the interaction among thin voxels for accurate offset regression. Then we project all the shifted thing points on the bird's-eye view image to generate the clustering pseudo heat map for obtaining instance information, as mentioned above. We also propose a center grouping module to handle redundant centers. The outputs of the two branches are merged to create the final panoptic segmentation results. Here we show some ablation studies. Firstly, the fusion of the fine-grained voxel features and the BV features brings 1.1% PQ improvement, which has more effects on the semantic branch. From this slide, it can be seen that our pseudo heat map outperforms the nerd heat map on both datasets. Note that our new sense, which contains more dense foreground objects, the semantic result drops significantly after being corrected by instance IDs generated from the nerd heat map. This suggests that the outputs of the nerd heat map are far from good. The reason is that the nerd heat map suffers from both the quality inconsistency and the position inconsistency, because the predicted centers and the shifted thing points come from two separate branches, while this problem is well solved by our pseudo heat map. We further analyze the accuracy of the offset regression, which is also a key factor for clustering-based panoptic segmentation methods. Since such studies can rarely be found in previous works, we adopt the average endpoint error to evaluate the results. It can be seen that our method has a significantly lower endpoint error, which shows a strong ability to segment objects that are very close to each other. Last but not the least, we achieved the first place on the public leaderboard of the semantic kitty and nuisance with real-time speed. Here we show some qualitative examples on nuisance. We use random colors for different instance IDs, and we also project the LiDAR results to images for better view. This slide shows the robust performance of our approach for a group of close instances, thanks to our proposed clustering pseudo heat map. And our method is also good at processing big objects. Thanks for watching.